Hey guys, today we're going to tackle fixed income VaR mapping. And honestly, this is one of those topics that looks terrifying in the book, but becomes super logical once you slow it down. So don't stress. We'll use just one simple example and solve it three different ways, step by step, like we're figuring it out together. Imagine we have a small portfolio with only two bonds. The first is a 1-year zero coupon bond worth 100 million, and the second is a 5-year bond, also worth 100 million, that pays a 5% coupon. So total portfolio value is 200 million. We're also given the VaR percentages for zero coupon bonds. 1 year is 0.496%, 2 years is 0.986%, 3 years is 1.484%, 4 years is 1.971%, and 5 years is 2.461%. Our job is simple. Convert this messy portfolio into something easier so we can calculate VaR. That conversion process is called mapping. Let's start with the easiest method. Think of principal mapping like the lazy shortcut. We basically say, forget coupons, forget timing, let's pretend all the money comes back at one average time. Since both bonds are 100 million each, they have equal weights, 50% and 50%. So the average maturity becomes 0.5 times 1 year plus 0.5 times 5 years, which equals 3 years. Now we just look up the 3-year VaR, which is 1.484%, and multiply it by the total portfolio value. So 200 million times 1.484% gives us 2.968 million. Done. Super fast. But also pretty rough because we ignored all the coupon details. Now, let's get a bit smarter with duration mapping. Instead of using maturity, we use duration, because bonds actually react to interest rate changes based on duration. After discounting the cash flows and doing the calculation, the portfolio duration comes out to 2.768 years. But we don't have a VaR number for exactly 2.768 years, so we interpolate between 2 years and 3 years. The 2-year VaR is 0.986% and the 3-year VaR is 1.484%. The difference is 0.498%. Multiply that by 0.768 and add it back to 0.986, and we get roughly 1.369%. Now multiply 200 million by 1.369%, and the VaR becomes about 2.74 million. Notice how it's already lower than before. That's because this method captures interest rate sensitivity better. Finally, we use cash flow mapping, which is the most accurate and also what professionals actually prefer. Here we stop treating the bond like one big block and instead break every single payment separately. That 5-year bond pays 5 million each year for 4 years and then 105 million in the 5th year. Each of these payments is treated like its own tiny zero coupon bond. After discounting to present value, we get approximately 104.83 for year 1, 4.63 for year 2, 4.42 for year 3, 4.24 for year 4, and 81.88 for year 5. Now we multiply each present value by its corresponding VaR percentage and add them up. If we assume everything moves perfectly together, we get about 2.674 million. But that assumes something unrealistic. It assumes all maturities move perfectly together, like they're glued to each other. In real life, a 1-year rate and a 5-year rate don't move exactly the same. Sometimes they move together, sometimes differently. That difference actually reduces total risk. And this reduction is called diversification. So instead of simple addition, we adjust using correlations. This is where the correlation matrix comes in. Don't panic when you hear matrix. It's just a big table that tells us how related each maturity is to every other maturity. A value close to 1 means they move together strongly. A value less than 1 means they don't move perfectly together. Now, here's the key idea. We take our risk list and mix it with this correlation table. Practically, what we do is multiply each row of the table with the risk numbers and add them. That's all matrix multiplication really is. Multiply and add. For example, for the first maturity, we multiply each correlation by each risk, add them up, and we get a weighted risk. Then we repeat this for all 5 rows. So instead of 5 independent risks, we now get 5 adjusted risks that already include how they interact with each other. Next, we combine everything one last time. We multiply those adjusted risks with the original risks and add them, which gives us a total of 6.840. Finally, we take the square root, and that gives us 2.615 million. That number is the diversified VaR. So notice what happened. When we ignored correlations, risk was 2.674 million. After accounting for correlations, it dropped to 2.615 million. Same portfolio, lower risk, just because the cash flows don't move perfectly together. So remember this intuition. First calculate each cash flow's risk, then adjust using correlations, then combine and take the square root. It's the most accurate method because it captures real diversification instead of assuming everything moves the same. And that's the whole matrix step. Nothing fancy, just multiply, add, and square root. Answer. So if you compare all three methods, principal mapping gave us about 2.97 million, duration mapping gave 2.74 million, and cash flow mapping gave 2.62 million. As we move from simple to detailed, the estimate becomes more realistic and usually slightly lower. That's the key takeaway, and that's fixed income mapping in the simplest way possible. If this made the topic click for you, you're definitely ready for exam questions on this. Catch you in the next one.